All right, welcome back. So this week we're going to be talking about number theory. And number theory is a very old subject, and it deals with sort of the simplest objects we could imagine, which are whole numbers, so integers. We don't have real numbers, irrational numbers, fractions, pi, square root of 2, all those things. We're just dealing with good old integers, right? And in dealing with integers, we know how to add, subtract, multiply, divide integers. There's a new property that we want to talk about, which is divisibility. So here's a definition. And I'm just going to assume everything we're talking about here are integers. So A is divisible by B if A can be written as B times C, where C is an integer. So A is divisible by B if it can be written as B times some other integer. And this is not at all a startling definition, right? 12 is divisible by 3 because 12 equals 3 times 4, right? 13 is not divisible by 3 because 13 is not 3 times 4, it's not 3 times 5, it's not 3 times any integer. So there's no integer C for which 13 equals 3 times C, so 13 is not divisible by 3. Okay, pretty straightforward definition, but everything we do is going to stem from divisibility. Okay, so another way to think of this is A divided by B is contained in the set of integers. That's a simpler way to look at it. We can also say that that B is a factor of A, right? And by a factor we mean that it's a whole number of times that B goes into A. We can also say A is a multiple of B. So there's an integer multiple of B which is equal to A. And we write this with a shorthand as follows: B divides A. So this means B divides A, or A is divisible by B. And this is not a slash, okay? This is not B divided by A. This is not B over A. None of those things. This is B goes into A. B divides A is a multiple of B. A is divisible by B. B is a factor of A. Okay? So we could write 3 divides 12. We would write 3 does not divide 13. Okay? Just notation and terminology, but it's really important because we're going to use this a lot. With this simple definition, okay, A divides B, A is divisible by B if A can be written as B times some integer. With just that definition, we can start spinning some pretty powerful proofs. So, for example, here's a theorem. If A divides B and A divides C, then A divides B plus C. And how can we show that this is true? Well, A divides B, we're given. And since A divides B, that means A equals B times some integer, which I'll call K1. We also know that A divides C, which means A is equal to C times some other integer, K2. Well, if A is equal to B times K1 and A is equal to C times K2, what can we say about B plus C? Can we show that A divides B plus C? So I'm going to start doing something. I'm going to put a little squiggly area over here and I'm going to say ignore. This is going to be my scratch area, but I want to make sure that my scratch area is separate from my proof area. Because I'm going to write things over here that aren't necessarily true. I'm going to write things that I want to explore. Okay? and try to get a feeling for what's going on. So I messed up over here, right? A divides B means that B equals A times some integer. Okay. A divides C means that C is equal to A times some possibly different integer. All right. So what I'm trying to prove is that A divides B plus C. So we want B plus C equal to A times some integer. I can't put that over here because I don't know if this is true. This is just kind of a scratch area, okay? Well, what do I know about B plus C? B is A times K1, C is A times K2. I know that B plus C is equal to A times K1 plus A times K2. And I can factor out my A, so it's A times K1 plus K2. And K1 plus K2 is an integer, so this is equal to A times K3, where K3 is an integer. And guess what? This is the definition of A divides B plus C. So a very direct proof, starting with this and this, I was able to prove this. So that's a nice direct proof. Let's look at another theorem. If A divides B and B divides C, then A divides C. So what's the proof? A divides B, that's given. I'll go ahead and number these. So since A divides B, B equals A times K1, K1 being an integer, that's definition of divisibility applied to statement 1. Statement 3, B divides C, that's a given. Statement 4, C equals B times K2, where K2 is an integer. That's the definition of divisibility applied to statement 3. Well, we know that B can be written as A times K1 and C can be written as B times K2, so let's substitute. C equals A times K1 times K2. And the reason for that is substitution of statement 2 into statement 4. And still K1 and K2 are integers. And so C equals A times K1, K2, that's just associative property, says we can move those parentheses. So it's associativity applied to statement 5. And then C equals A times K3, where K3 is an integer. And that's just properties of integers applied to statement 6. Well, we've just proven that C is equal to A times some integer. And therefore, A divides C. That's the definition of divisibility applied to statement 7, and that is what we were asked to prove, A divides C. So a direct proof that this and this implies that. So we can do lots of direct proofs like this related to divisibility, and we'll do more of that in a bit. But I need to introduce a second concept, and it's closely tied to divisibility. And this is the concept of modular arithmetic. Now there's a very formal mathematical explanation of modular arithmetic, and it has to do with something called the division algorithm, which is a very powerful theorem about integers. But I don't want to motivate this using all of that machinery. I want to give you a very sort of matter-of-fact definition of what we mean by modular arithmetic and modular equivalence. So we're going to use this symbol that we used for logical equivalence, but when we're talking about number theory, this means something totally different. So we're going to write A is congruent to B, and this is going to be what we say modulo some integer m. and this means m divides a minus b. So this is our definition of congruence. A is congruent to b mod m means that m divides a minus b. So for example, 13 is congruent to 4 modulo 3 because 3 divides 13 minus 4. What's 13 minus 4? It's 9. 3 divides 9. So 13 and 4 are congruent. Modulo 3. Modulo 4 13 is not congruent to 4 because 4 does not divide 13 minus 4. 4 does not divide 9. Okay, so we're going to work with this property a lot, this idea of modular arithmetic. 13 congruent to 4 mod 3, 13 not congruent to 4 mod 4. 16, on the other hand, is congruent to 4 mod 4 because 4 divides 16 minus 4. 16 minus 4 is 12, and 4 divides 12. Okay, so it may not be clear why we're doing this, but I want you to be clear what the definition of congruence is. It means that the difference of these things is divisible by m. Okay, and you can probably convince yourself that if a is congruent to b modulo m, then b is congruent to a modulo m. Because if a minus b is divisible by m, b minus a is certainly divisible by m also. It's just going to have the negative of whatever the factor was when you divided a minus b by m. Alright, well, another way to think about this, and this is sort of the more intuitive way, a congruent to b modulo m means a, let me use the old-fashioned divide symbol, a divided by m and b divided by m have the same remainder. So let's look at 13 and 4 mod 3. 13 divided by 3 is equal to 4 with a remainder of 1. 4 divided by 3 is equal to 1 with a remainder of 1. These remainders are the same, therefore 13 and 4 are congruent modulo thingy divided by 3. And you can convince yourself that that if this is the case, if a divided by m and b divided by m have the same remainder, then a minus b must be divisible by m. And we'll do some exercises on the board seeing that. Alright, so why are we doing this? Well, that's the topic of the next video, which is why modular arithmetic is useful. But basically, the idea is there's an infinite number of integers, we know that. But sometimes, if we work modulo some number, we can prove things about the whole set of integers by only looking at integers modulo some number m. And since this congruence is based on the remainder when we divide one number by another, there's only so many remainders that you can have when you divide by m. In fact, there's exactly m minus 1 remainders possible. So in a nutshell, modular arithmetic is sometimes going to let us take problems about the totality of the integers and reduce them to problems about a very small subset of the integers. One last comment though, this business of a remainder is something we need to be very careful about. So let's look at mod 3. And I can make the statement 17 is congruent to 2 mod 3. 17 divided by 3 has a remainder of 2. 2 divided by 3 has a remainder of 2. But it's possible that we could do the following. We could say 17 divided by 3 equals 5 with a remainder 2. We could also say it's equal to 4 with a remainder of 5. 4 times 3 is 12, plus 5 is 17. Or it's equal to 3 with a remainder of 8. Or it's equal to 2 with a remainder of 11. Or it's equal to 6 with a remainder of negative 1. So the notion of remainder is not necessarily unique. And if we note that 2 divided by 3 is equal to 0, with a remainder of 2, and if we wrote 17 divided by 3 like this, we could say, hey, that's got a remainder of 11, remainder of 2. They're not congruent, right? It's only when we look at this, 5 with a remainder of 2, that we see the remainders are the same. So remainder of 17 divided by 3 must be some number bigger than or equal to 0 and strictly less than 3. And more generally, when we talk about the remainder of A divided by B, it must be some number bigger than or equal to 0 and strictly less than B. And as long as we put this requirement on what we mean by a remainder when we do a division, then our definition that we just had will be valid. This idea that A is congruent to B means that A and B have the same remainder when you divide by whatever modular you're working in. All right, so we'll start from there next time, and we'll go ahead and start seeing properties of arithmetic when we work over a modular system.